Eitan's talk will be wonderful today, so welcome, Eitan.
And one thing I'd like to add to Alex's intro is that I did my undergraduate here in the engineering science program. So, for example, Stuart Smith was my calculus professor, and I recognize some of the other faculty as being my professors or professors we gossiped about from the undergraduates. And it's I came back once when Stephen Morris organized the Fields Physics Math Colloquium, and I had a pleasure to speak there. But I haven't been back countless times to speak, so it's a very special opportunity for me to be back home and to be able to share some of the work I've done. And I called the talk a geometric perspective on computing motion, but a more lighthearted title might be From Sorcery to Science, Hollywood Physics as Computational Engineering. And I hope to share with you how kind of a mixed background in computer graphics as well as engineering has come together. And of course, if you've been a professor for 15 years or so, you've done a lot of projects. And rather than try to cover a lot of projects at a very high level, I want to just talk you through one arc of work so you can kind of see it from birth through the end. And then if time permits, I'll share with you a little bit about other topics, but probably time won't permit. So to start, we need to go back a long, long time, 40,000 years ago. Here is a painting I found inside a cave in Spain. It's a number of such paintings and wall scratchings dating back to 40,000 BC. And you could interpret this as a painting of an 8-legged boar, or you could say that somehow the artists were trying to depict motion in the best way that they could at the time. And in the 3rd millennium BC, there was a vase which was uncovered by archaeologists, and it had this drawing on it, which I've unrolled here onto the page for you to see. But of course, it's on a vase, so you can keep turning it. And it's basically, again, telling the story of a goat that jumps up to get some fruit or lick a leaf or whatever it is that goats do. But it's, again, trying to depict motion in the best way that was available at the time. Now, in modern times, I guess, what we associate with depicting motion, or at least what I do, is the work of studios maybe most closely identified with Walt Disney, where they drew many frames of an animation and flipped back and forth between them in order to tell a story. And the earliest full-length such film was Snow White and the Seven Dwarfs. And there's a lot of physicality to the motion of the characters. You can see the inertia, you can see the elasticity, you can see dissipation. You can see a lot of physics in there, but at the same time, there's a lot of storytelling and emotion. So it's this kind of mix of capturing art and physics. And up here, what I have is one of the typical exercises that is still given to animators. And this is because Disney didn't hire illustrators that were trained in anatomical drawing. Rather, he hired newspaper cartoon artists that could tell a story. And then he trained them in kind of a bit more of a maybe realistic sort of rendering. And he said, here's a sack of flour. I want you to retain the qualitative physical aspect of a sack of flourness while giving it different poses that suggest different emotions or different actions. So this is somehow retaining the qualitative aspect of a physical system while telling a story. And today in computer graphics, if we're interested in depicting motion, we have a bunch of computational goals. We want algorithms that are efficient, so they're economical to execute. We want the algorithms to be reliable, so artists get very frustrated if you have to set certain parameters, and after you set those parameters and wait a day to get the output of your simulation, the output is meaningless. So we want this kind of reliability. And we're doing this inside a creative context, so we want to keep that in mind. And I like to add that we want the algorithms to be simple. And the reason for simplicity, well, of course, from a mathematics perspective, it's just more elegant if we can do it more simply. But from a very pragmatic perspective, people are more likely to pick up and use your work if they can understand it and if they can put it to practice quickly. Everyone has different approaches to addressing these goals. One of my loves from a long time ago is geometry, and so I use computer graphics as an excuse to study and apply geometric ideas. So I put up pretty images, but the fun part for me in the research is learning new geometry. And so my strategy is to look for geometric insights into the problems. So one way to say that is to ask the question, how do we describe the qualitative aspects of a physical system? And the answer that I'll be kind of walking through today is to follow the geometry. So what do I mean by that? Well, here's, for example, planetary motion, and there's a bunch of ways we can describe planetary motion. Of course, you could write down the gravitational laws, you could write down an ODE, set up an initial value problem, or a system of ODEs, and then step forward through this with a numerical integrator. But Kepler had a different view of describing planetary motion. Kepler said if you position the sun somewhere, and you position a planet somewhere, and you consider the radius connecting the sun to the planet, and you consider some finite interval of time, and you look at the area swept out by the radius, then if there are two equal finite intervals of time, you will get the same area. And that is how Kepler's second law characterized the motion of the planet. Now, does anybody know who proved Kepler's second law?
Newton.
Very good. Professor Stephen Morris, that's right. In the Principia, Newton had a proof, and it looks like this. This is actually a copy of his proof. The sun goes on the bottom left. And what's immediately remarkable to me about Newton's proof is that it is a discrete proof, not a continuous proof. Right? You can see that just from the drawing. And if you position the planet somewhere, then Newton said, well, the planet will basically continue in inertial motion undisturbed in the absence of external forces. But we're going to treat the action of the sun as a periodic impulse as opposed to a continuous force. So at regular clock ticks, the sun is going to be pulling the planet, and since it's an impulse, it's going to cause an instantaneous change in velocity. And so the perturbation in the trajectory of the planet will, of course, be parallel to that impulse. And basically, Newton argued that just from this line being parallel to this segment, and so on for this one parallel to that, just by the simple argument that if you translate one corner of a triangle parallel to the base of the triangle, you don't change its area. By just composing three such arguments, you get that each of these triangles must have the same area. So he proved a discrete version of Kepler's second law. So one could say that the connection between mechanics and a geometrical view of mechanics, or a connection between mechanics and geometry, has been studied for centuries, at least in a classical sense. So what we're doing today is we're asking, how does this connection impact how we compute? And that's the question. So if we bring up again Newton's proof, but let's just zoom in on two triangles, and let's label the picture. So I've labeled it with position and momenta and time step variables. I've assumed mass equals 1. Then, and the perturbation is up there. Then we can directly read off from this picture the relationships. You know, this position is equal to this one plus this vector, for example, right here. Same thing for the momentum update. So we can read off an algorithm that we can execute that's just following Newton's proof, line by line. And if it does so, it must be that these triangles have the same area, because we're exactly following Newton's argument. So how does such an algorithm perform? Well, what I have here is a comparison that I did not prepare. It's from the textbook on geometric integrators by Herr, Ludwig, and Bonner. And on the left, I've put down explicit Euler. which is the simplest time-stepping algorithm that we teach in numerical methods. And on the right, I've put down symplectic Euler. Okay, and we can compare their performance. Let's call attention to the time steps. We're running explicit Euler with a factor of 100 smaller time steps. So we're giving it an extra chance to win here in terms of accuracy. But as you know, explicit Euler is not a stable algorithm, and so after enough orbits, the planet flies off to Alpha Centauri. On the other hand, what happens with symplectic Euler? Well, the analytic trajectory is shown here by the dots, so we're not tracking it perfectly. But in a qualitative sense, we're still tracking the shape of the orbit. Right? And you might say, that's very nice, but I have BDF2 and Runge-Kutta 4 and my favorite implicit integrator. What's interesting here is that these two integrators have the same computational cost. They're both explicitly evaluatable. And the one that's giving us capturing the geometry is doing so at larger time steps. So there's something here about distinguishing between what we think of as convergence arguments, for example, for finite elements, sublove spaces, and so forth, and talking about what happens at the discrete level, even for arbitrarily coarse discretizations. We're retaining some part of the inherent geometry of the system, even for coarse discretization. And it extends beyond just the qualitative view of these orbits. Here we have some comparisons for the energy behavior and the global error of the solution. Okay, the global error of the solution, it's not surprising that explicit Euler has terrible global error because we saw that the planet can fly arbitrarily far away. So it's not surprising that in some sense, if you're always remaining elliptical and nearby, you're going to have some small error. But the energy is very interesting, right? So explicit Euler is rapidly growing in energy. Symplectic Euler is not conserving energy in a strict sense. It just does not have a systematic drift of energy. So from a coarse level, it looks like it's preserving energy. And actually there are proofs of this for symplectic integrators for Hamiltonian systems that say that for the discrete system, it is exactly interpolating the trajectory not of the original Hamiltonian system that you discretized, but of a slightly perturbed Hamiltonian system. Therefore, if you measure the energy using the expressions for the Hamiltonian that you started with, you're not going to see exact energy preservation, but you're always going to see something close. And that's desirable. So that's kind of the motivation for including geometric considerations in our algorithms, especially when we're interested in capturing the physics qualitatively. Now, we are interested in this not only in the temporal setting, but also in the spatial setting. And in the spatial setting, the natural language for us to turn to is classical differential geometry, the study of curves and surfaces. It's the mother tongue of mechanics. Most mechanical systems of interest can be expressed in terms of divergence, curl, curvature, all of these quantities that we know and love. And there's also this view of differential geometry as a study of invariants and symmetries. You know, this is the Erlangen program. And that's going to be important and inspiring for the kind of approach we take. So we can't work directly with the classical differential geometry because we're working with discrete systems. We don't have smooth curves and surfaces. Our surfaces and our curves are made from point samples. And a lot of the definitions that one would want to just immediately apply will simply break down. So what we want to do is recognize that we're working in a discrete setting and turn to the idea of structure preservation. Namely that if we take specific theorems or specific relationships that hold in the classical smooth setting, we want to rebuild those relationships so they hold exactly in the discrete setting, not just in the limit of refinement, but for arbitrarily coarse discretizations, as we saw for Kepler's second law with Newton's proof. And if we do that, we then want to expect some discrete notion of conservation and balance laws, as we saw before. So that's a lot of words. So let me walk through a very pedestrian example to get us all on the same page. And This example is going to take longer than you would like for some people in the audience, and less than you would like for other people in the audience. I'm trying to strike a sweet spot because we have a broad audience. But hopefully it helps to give you a flavor for how we approach this. So let's talk about curves on the plane, and let's also put an arrow on them so we have a sense of traversal, we have an orientation. Then one thing we can do is, for any point P on the curve, we can fit the kissing circle, the best fit circle, or the oscillating circle at that point on the plane. And we can ask for its radius, and the inverse of the radius is going to give us the curvature. And in fact, we can assign, if we have a sense of traversal for the curve, then we can say that the curvature is positive or negative, depending on whether the circle appears to our right or to our left as we traverse the curve. Now, this curvature is an inherently local quantity on the curve, but it can be related to some global aspects of the curve. To do that, let's think about the Gaussian image of the curve. So for every point on the curve, if I think of the tangent to the curve, I can rotate it 90 degrees counterclockwise relative to the sense of traversal. I get a unit normal vector, and I can identify that with a point on the unit circle. So now my entire curve maps to some traversal of the unit circle. And if here's an exercise for this. If the curve is a straight line, then the normal is constant, and so I just get a point on the unit circle. And if the curve is kind of going straight and then rapidly turning and going straight, then I'm going to spend a long time here, and then I'm going to go rapidly here, and then spend a long time there. In fact, we can express the curvature as the relative speed between motion on the unit circle versus constant speed motion on the curve. So if I move at a constant speed on the curve, I can go faster or slower on the unit circle. And that ratio is one way to define the curvature. So I said that we can relate this local quantity to a global quantity, and to do that, we can consider closed curves, and we can look at the Gaussian image of these closed curves. And if the curve is closed and smooth, then we expect to have complete coverage, not complete coverage. We can have some closed traversal of the unit circle. For example, here we circle it 1 time, here we circle it -1 times, +2 times, or in this case, 0 times. But it's always going to be an integer number of times. And we have this idea that it's always an integer number of times if it's a closed curve. And we also have the idea that the relative speed between this picture and that one is the curvature. So if you put these two ideas together, you can show that the integral of the signed curvature for a closed curve is always an integer multiple of 2 pi. It's kind of how we might motivate a connection between topology and differential geometry in some sense, right? So for these closed curves, you have the example of the resulting integral. And it's interesting because if I wiggle around the shape of this curve, locally I can change its curvature. But of course, in general, I won't change the integral because the integral has to change by quantum jumps of 2 pi. So when does the integral change? It changes when the wiggling around goes through some kink or through some non-smooth situation. Otherwise, it stays the same. It's a nice relationship between the local quantity and this kind of global invariant. So we might choose that as the structure that's interesting to us. And then we'd say, okay, now we want to work on computers in the discrete setting. And we don't want to recover the structure just in the limit of refining. We want to build the structure in at the coarsest level. So we're going, we could use splines or something higher order to discretize a curve. But for me, aesthetically, that's not my aesthetic. The aesthetic is to work in the most discrete level possible and try to identify how these structures come back in. So I think this is almost a constellation of some kind. It wasn't intended to be, but This is not an astrology talk. But okay, this is my curve. And I'm going to use the terminology vertices and edges. And you could say, how do we define curvature? And just to drive home the point, if we define it by a best fit circle, we're not going to get very far. At least not in the smooth sense, because if I pick any point here that's somewhere on the straight edge, the best fit circle has infinite radius. And if I pick it right at a vertex, there is no best fit circle, or you could say it has 0 radius. It's kind of meaningless. And the reason for that is a lot of times when we move from the smooth to the discrete setting, we have to switch our thinking from pointwise to integrated quantities. We have to think not of curvatures in a pointwise sense, but as integrals of curvature over some region. And of course, if you remember your differential geometry, integral of signed curvature over some section of a curve gives you the change in angle of the tangent between the start and end. And so that inspires this kind of definition here, where we have a traversal of the curve. And if we start on this end, every time we reach a vertex, we have to make a turn by alpha, alpha 1, alpha 2, and so forth, and they have signs. And just adding up the sum of these turning angles is what I'm going to call my total signed curvature for the discrete curve. Now, repeating the exercise from before, I can also think now of what does the Gaussian image look like for this discrete curve. If I look at this, I can look at it literally. At an edge, the tangent is constant. So edges have a constant normal. So edges map to a point on the unit circle. And so consecutive edges map to consecutive points on the unit circle, and therefore the vertices correspond to these arcs of transition between points. And so we have this thing that we see sometimes in combinatorial geometry and in computational geometry, which is this duality where edges map to points and points map to edges in some sense. And that's one of the themes that recurs in this kind of work here. But anyway, once you have this, you can again count, if you have a closed polyline, then you're going to have, again, some closed traversal on the unit circle, and so you can count the total number of turns, and it's going to be integer. And so now you can almost trivially write down the discrete theorem, which holds, which is that the integral of total signed curvature for a discrete curve is going to be an integer multiple of 2 pi. And actually, the discrete theorem is in some sense even easier to prove than the smooth one, at least the special case, right? We learn in high school that the sum of exterior angles of a polygon is 2 pi. So it's just a generalization of that idea. This is awesome. We're done. The talk's over. Thank you, and have a good lunch. Well, what makes this line of research fascinating to me is that when you go to the discrete setting, there is no one discrete differential geometry. Of course, in the smooth setting, we know what curvature is, and we can look at it from different angles, different perspectives, and they're all equivalent. In the discrete setting, generally speaking, when you pick one of the perspectives to hold exactly for a discretization, you lose the equivalence to the other definitions. You only recover it in the limit of refinement. So you have these different discrete differential geometries depending on what you care about. For example, here's a simulation we did of a soap film. And so it's a soap film between 2 rings, and you get this catenoid shape. And I guess the mathematicians in the audience are thinking, okay, soap film, Hilbert geometry in the imagination, minimal surfaces, mean curvature flow, right? And so if you think that route, what you're thinking is of mean curvature as the gradient of surface area. And so when you have a minimal surface, a surface that has least area, you have it when the mean curvature vanishes. You have no more gradient flow to do. Well, if you apply that definition to curvature, you get a definition of discrete curvature that involves sine of theta over 2, as opposed to just theta. So you get a different expression, 2 sine theta over 2, which converges to, both definitions converge to the same thing as you refine the curve, but in the discrete setting, they have different properties. One comes from this variation of surface area or variation of length, and the other comes from the turning number theorem. So this tells us that each application that we look at requires that we ask, or sometimes ask around, for the relevant geometric structure. And so a lot of the way I approach this work is that when I get interested in a certain topic, I find physicists or mechanicians or mathematicians that know about that area, and I start to uncover what are the relevant geometric structures and kind of build something from there. So here's an example of that, and this will be maybe a little bit of a higher level. Pre-tenure, I worked primarily on surfaces. I had these projects on discrete shells and simulating cowboy hats and simulating clothing on heroines in Disney movies. You're not supposed to say princesses anymore. You say heroines because it sells better. And so I thought, okay, differential geometry is the study of curves and surfaces, and I haven't done any curves. So we started looking at curves. And the prototypical thing that we start thinking about with curves is these Courseratte rods. So these elastic curve-like bodies that occur at any scale from DNA to telephone cables to deposition of internet communication cables on the ocean floor. And there's a rich theory for elastic rods by Courseratte and by Kirchhoff, and I won't go into it right now, but our work is based on that. What I will say is that you have a competition between bending and twisting. So bending requires some notion of a strain due to bending, which comes from curvature, which we briefly discussed when we looked at discrete curves. But twisting requires some notion of twisting, which we haven't discussed. And that gets really interesting. And if you think about it, I hope I don't lose my presentation. I probably will. I did. This cable might be safer. This always happens. That's my family. How do I start this? There it is. Okay. If I take this shape here and I start twisting it, the material resists twisting, and it does so by moving into a configuration that is somehow less twisted. But in the process of being less twisted, that configuration is more bent. But it doesn't want to be too bent, so it finds a balance between being bent and being twisted. And that's the sort of balance I'm talking about, and you can get some really pretty behaviors. So this is a simulation of kind of a Twizzler being turned at one end, and you're getting this competition between twisting and bending. And so you might say, okay, I get it. You moved from surfaces to curves, so you just want to represent a curve in space and then do your stuff. Well, a curve on its own is not a sufficient representation, because consider this being a straight line, if I held it straight enough, and consider that I applied twist. Now you can't see it, because I'm very strong, but I can feel a force here pulling back on me. So this configuration is different than this one, even though they're both described by the straight line. And so what's different is the arrangement of the material, or the material cross-sections about the curve. And mathematically, that means that we want this notion of an adapted framed curve. So an adapted framed curve is going to be a curve plus an orthonormal frame decorating this curve. Every point on the curve maps to an orthonormal frame. Not just any orthonormal frame. We're going to discount the possibility of shearing along the direction of the curve, because we don't need that. And so this means that the tangent vector, which is not being drawn, is always parallel to one of the axes of the orthonormal frame. And so the other two axes are these two perpendicular ones that here I see spinning around, which intuitively tells us this thing is twisting, right? Intuitively, that's what it tells us. But how do we really go beyond intuition and talk about this? Well, Cartan's view was that we take a ride on the roller coaster, right? So Cartan's view was, if you traverse the curve on the frame, and examine the evolution of the frame from the perspective of the frame, then you will see how much the frame is rotating left or right. Okay, and that's going to give us your notion of twist. So here's another illustration for why this framed curve is necessary. The only boundary conditions I'm applying here are fixing the endpoints and twisting one of the ends. So to apply such a boundary condition, clearly I need to be prescribing the frame at that end of the curve. And then these plectonemes form. In fact, what you saw here was, to our knowledge, I've lost where I am. To our knowledge, the first animation for the merging of plectonemes, which is something that biologists apparently care about, which is how these two double helical structures merge into one over time. Now,
but now you have a third energy, which is that the curve wants to stay away from itself.
That's right. So there's contact modeling here. And if Alec can grant me another hour, I have a lot of material on contact modeling. It's one of my favorite topics, but I have to skip it. So it's there, and I'm not telling you about it. So, the reason we've been doing this exercise is that, as a reminder, we're trying to look for what is the important structure for us to capture and carry over to the discrete setting. And one way to think about this is to say that one way to measure twist is to start from something that has no twist and measure the change away from that. So you need some kind of origin or baseline. And so consider this exercise where I have this curve and I put a lot of beads on it, kind of like the children's toy where you can slide beads around. So it's filled with beads. And I put a little bit of elastic glue between the beads, so the beads don't want to turn relative to each other, right? But the beads are free to rotate around the curve. They don't want to rotate relative to each other, but there's no friction stopping them from rotating about the curve. This means that if I position this curve in any configuration, the beads will minimize kind of their discrepancy to each other while adapting to the shape of the curve. And this is what we call the twist-free, right? The minimally twisted or twist-free configuration. And, maybe the first time I said framed curves, the geometers in the audience probably said, I know, Frenet frames, they're great. So Frenet frames are very useful, but they're not the right structure for this notion of a twist-free frame. Instead, what's the right structure, according to Langner and Ziegler, is this natural, parallel, or bishop frame. And it's given by the ODE that says, start with a frame at one end of the curve, and move it along the curve in a manner that's as parallel or as natural as possible. So you always have to rotate it enough that the tangent matches the curve, but you don't want to introduce any extra rotation.
So
whenever you have this kind of ODE,
so parallel transport? Is that parallel transport?
I will bring the connection up in one slide. So it is the parallel transport that you're thinking of, yes? But of course I'm not presenting it that way yet, right? So the requirement is that there's no twist about the tangent, and that the tangent of the frame must stay, or the vector representing the tangent for the frame must remain parallel to the tangent of the curve. And in Cartan's view of moving frames, we can represent this as this arc length derivative or time derivative of these two vectors, u and v, by saying that they evolve as some Darboux vector cross product the actual frames. And in this case, the Darboux vector is the curvature binormal. So kappa here is the curvature, and b is the vector binormal. So if we evolve in that way, we always rotate about the binormal of the curve, then we have this nice graphic here that we're as twist-free as possible. So the question was, are you using parallel in the same sense as we think of for vector fields, vectors on surfaces? And the answer is yes. if you take the tangent vector of the curve, instead of the Gaussian image, we're going to think of the image of the tangent indicatrix. So we take the unit tangent vector on the curve, that maps to a point on the unit sphere. That means that the whole traversal along the curve maps to some traversal along the sphere. But of course, this black vector here, the u vector, is perpendicular to the tangent vector. And since the tangent vector is a radius of the sphere, a vector perpendicular to it lies on the surface of the sphere, right? So now we have what we're used to thinking about, which is a vector on the surface of the sphere. And if we think of all the tangent vectors on the curve, that gives us a traversal of the sphere. And now we're thinking about parallel transporting a vector along some curve on the surface. And that is exactly how the frames evolved. So yes, was that your question?
I guess so. It's also parallel transit in R3.
Well, it has to remain adapted.
Right, sure.
So it's always rotating. I guess in Euclidean space, you just move the frame without any rotation.
Right.
Yeah. So this is the structure. So now I've gotten kind of to my punchline. Yay. Right, the thing that I care about discretizing in this case is parallel transport of frames along curves in order that I can come up with a discrete definition for twist. I already have my curvature, then I'll have my twist, then I'll have my model. So a lot of the talks we give have a slide like this that summarizes kind of the structure that we like and says now we need to build a model from discrete building blocks. And so here now we have again our discrete curve. But now I'm attaching frames to it, and I'm showing you kind of the discrete ODE that's laying down parallel frames starting from one end to the other. And what I want to call attention to, as before, our frames are just, our curves are just vertices and edges. And almost as before, I guess, as we saw, we have this kind of duality where for every edge, we have one frame. And then at the vertices, we have this kind of smooth rotation of the frame. So this kind of same thing we saw with the Gaussian image before. And what's the definition again? No twist about the tangent. The frame must stay adapted. And so basically at every vertex, we must rotate about the binormal. That is, take cross product of the two edges and rotate about that. If the edges are parallel, no problem, because we're rotating by the curvature binormal. So when the edges are parallel, the binormal may not be defined, but the curvature binormal is defined. It's zero. There's a zero rotation. So it's a nice, well-defined way to set this twist-free frame. Okay. That's, and by the way, it has the same equivalence to parallel transport, where you're basically now each edge, which has a frame, maps to some point on the unit sphere, because each edge uniquely defines a tangent. Each vertex corresponds now to a great arc on the unit sphere between consecutive points, and now we're just parallel transporting across these sequence of great arcs. So that's the basic idea for how to preserve structure for twist in this model. And I think what I want to do with the remaining time is just show you a little bit of the ways in which it's being used. We have what, 10, 15 minutes, is that right?
Yeah.
Okay. This is a little exercise that what Peter Jackson's studio did when they were starting to work on The Hobbit and so forth, where they're putting the hair through some test runs. And this is the final use in Disney's Moana, where the main characters all have a lot of curly hair, and it's all being animated using this approach. And this is the Jungle Book, and the trees are being animated using this approach so that the artists don't have to move them one by one. And this is Adobe Photoshop and Illustrator. For a number of years now, they have paintbrushes that operate in real time where the bristles bend and flex, and all of these are discrete elastic rods that are allowing this kind of realistic deposition of the paint. Here's an experiment, a little demonstration that we did, where you take a slinky and you stretch it out and then you hold the ends fixed, and as you bring it back together, you get these two helices of opposite chirality. This is called the helical perversion, and the simulation can capture this. And in fact, you see this in nature. I think this is your photo.
My photo.
It is your photo. And you see these kind of helical perversions happen here, so it happens in real life. And in fact, Sharon Gerbaud and Mahadevan and their co-authors have a science paper where they built on this computational approach in order to analyze the growth of cucumber tendrils. There was researchers, not us, at UC Berkeley and Chapel Hill and Johns Hopkins, who used our model to simulate steerable needles. These require either operation by robots or by highly trained surgeons because they have a beveled tip, and as you insert them, they twist, and so you need a lot of training to use them, and so they use that model. Soft robotics, there's work by Paley and others on making caterpillar-type robots that don't have rigid joints. So in order to predict the dynamics of these, they built on the discrete elastic rods framework. In fact, O'Reilly, who's one of the authors here, is a mechanical engineering professor at Berkeley who wrote a number of textbooks on thin shells and elastic rod modeling. And he just came out with a book. He notified me about it after it was done, called A Primer on the Kinematics of Discrete Elastic Rods, and he basically read our paper and said, I want to introduce this to the mechanics community. So he did that. Now, we also directly collaborated with physicists. With Pedro Rice, we looked at propulsion of flagellar organisms. And we used our model to kind of look at the different phase diagrams for this kind of propulsion. And it's never been fully understood how these guys turn. Because they really only have one control, which is the speed at which this helical flagella operates. But if you run simulations of this, you see that above a critical rotation speed, the thing becomes chaotic. It just starts flailing around. And you no longer have control over which way you're going. You start going in any different direction. And if you look at the actual measurements for these organisms, there will always appear to be operating at a rotational speed that's just below this chaotic regime. So the hypothesis could be that whenever they want to turn, they just slightly ramp up their speed just a little bit in order to change the direction. That's the hypothesis. The other thing that we did, inspired by some experiments that Stephen Morris was doing in his lab here, is we looked at the deposition of cables on the ocean floor and of serpentine deposition of carbon nanotubes. And these are operating at very different scales, but it's a very similar mechanism, which is just by depositing on a substrate that's moving slower than the rate of deposition, there's some pattern that forms. And so Pedro built this conveyor belt experiment where he was basically depositing the cable faster than the belt could absorb it. And here's comparisons of the experiments and the simulations showing two of the patterns that can emerge. We classified all of the patterns in a phase diagram and also came up with some surprising results for what happens here. And this was published together with Pedro in the Proceedings of the National Academy of Sciences a couple of years ago. And I mentioned the experiments that Stephen Morris conducted here at U of T, and these were with silicone oil and also with Lyle's golden syrup, right? One is tastier than the other. And so, you know, one of my collaborators, Basile Duli, mentioned, you know, once you have a discrete elastic rod model, you basically have a stress-strain relationship. And for viscous materials, you just make it a stress versus strain rate relationship. You have to add a few other bells and whistles like surface tension, but the basic thing is just the moving over from stress strain to stress strain rate. And so we did that. We took the elastic rods model and made a discrete viscous threads model that can reproduce these patterns. This was published in the Journal of Computational Physics as well as at SIGGRAPH. And we recovered a lot of the patterns that are observed. There's a couple that we didn't recover, and we think it may be due to contact, that other term that was raised before. I think these patterns are really cool because my husband is a pastry chef, and he spends all this time going around in circles. But this way you can just move, if you just get the right speed at which you move. But my friends tell me that you can use it to make stretchable electronics and wearable electronics and boring stuff like that. So I want to end, do I have like 5 more minutes? Okay. So I want to end with this kind of, I think, result that in some ways ties up some of the ideas we've been discussing. In an even simpler setting, I want to talk about the Laplace and Laplace-Beltrami operators. And I've put, these are slides for a graphics audience, but you can use your favorite physics applications of these operators. The point is that everyone uses Laplacians in some way in their work. In data science, maybe for smoothing and denoising. In graphics, it may be for parameterization or mesh editing, or it may even be for simulation, certainly for modeling physical phenomena. And if you open a standard textbook, you're going to get lots of properties of the Laplace operator. It's going to be symmetric in the sense of adjoints. It's going to be local. This one's usually not written down, but it's important for me. So it's local in the sense that changing a function value far away is not going to change the Laplacian here. It only sees what's right here. It's going to, come back. It's going to obviously have constants in its kernel, but also if you're on the plane and you think of a linear function on the plane, then it's going to have the linear functions on its kernel. Right? Obviously that picture changes when you're on a curved surface. Also, solving Laplace's equation can be thought of as minimizing an energy. So it's positive semi-definite. And there's the maximum principle that says that any local maximum must appear on the boundary. Right? So that's an important concept, for example, for the heat equation. So what we did is we looked at discretizations of the Laplace operator. And not just in graphics, we looked broadly. So we looked at finite elements, we looked at graph theory approaches, we looked at the work of Bobenko and Pinko and others in the math department at TU Berlin. And we kind of categorized them. And notice that if you write down discrete analogs of the properties of symmetry, which now becomes a matrix symmetry, locality, which talks about the sparsity structure of the matrix, linear precision, which talks about linear functions being in the kernel of this matrix, and positivity, which means that the off-diagonals of this matrix are positive and the diagonal is negative, which basically implies both the positive semi-definiteness and the maximum principle together, so it's a stronger condition. And what we notice is that if you look at all of the existing Laplacians, they're all missing one feature. They discard one feature for the others. So we thought we were really smart, and we're going to make a perfect Laplacian, but we failed. And instead, what we came to realize by digging around and eventually actually going back to work by Maxwell, of Maxwell's equations, and Cremona, Luigi Cremona, geometer, and also of Arnhammer, is that there is no possibility to satisfy all of these properties for an arbitrary mesh. And so there's a no free lunch theorem that we established that basically says that for an arbitrary triangulation, it could be of the plane, it could be of, it could also be curved. If you want to write down a Laplacian as a linear operator there, you're going to have to drop one of the properties for the others, which kind of makes a stronger statement saying that each application requires that we ask for the relevant geometric structure. And then we went further than that And we actually said, well, are there meshes that do allow for a perfect Laplacian that has all those properties? And the beautiful answer there is that yes, there are. It starts with Delaunay triangulations, but it's not limited to Delaunay triangulations. Any regular triangulation, which is basically any triangulation that can be viewed as a weighted Delaunay triangulation, admits a perfect Laplacian, and only those triangulations admit perfect Laplacian. So I think in the interest of time, I do have some slides on contact. I'm happy to talk to you about them offline. Some slides on symplectic structure and a bunch of other things that I didn't get a chance to talk to. But so that we wrap up on time, I'm going to thank you very much. And again, it's a real pleasure to have this opportunity to be here and talk with you.
Thank you very much, Eitan. Questions?
And I think I'm going to leave eye candy of stuff we didn't get to talk about while we discuss questions.
Steven.
Two comments. The tendril perversion is actually discussed by Darwin.
That's right. That's true. They went back to Darwin.
Yeah, and the question is, if left-handed helices are selected somehow, how come you sometimes see little patches of right-handed? And it fascinates Darwin as to why this thing appeared like that.
That's right. I think they mentioned that as the inspiration for their work.
Yeah. And the second comment is that the viscous thread experiment is no longer in Toronto. It's now in Mexico City, where my collaborator is working on the non-Newtonian version.
Oh, that's interesting. Well, I'm always up for a trip to Mexico.
So I suppose you can add terms to your elastic plastic model to make the thread non-Newtonian. And off you go.
I guess there's an extension of Vera's in Mexico, but not in Mexico City, right?
I don't know.
Oaxaca.
In Oaxaca, yeah.
The motivation is in part due to the painting of Jackson Pollock. It turns out that you can show by watching movies of Pollock, you can watch the speed with which he moves his hands and the height and so on.
Oh.
You can show that over the course of his learning how to drip paint, he moved to a parameter space which did not allow the coiling or meandering of the paint.
Oh.
So some of his early drip paintings have little curly cues and meandering in them, but he eliminated those intuitively by moving his hand faster and by using different viscosity scenes.
That's neat.
So my collaborator in Mexico studies the fluid mechanics of painting.
You should put us in touch.
I will.
Awesome.
Other questions? Can you give us a hint of what you're up to next?
So right now I'm working on granular materials. Granular materials are, I think, second most handled material in industry after water, but they're very challenging numerically. In order to do anything meaningful with granular materials, you have to work with, a billion grains, at least millions of grains, and it's just computationally intractable. So what people do is they homogenize the problem and they look at continuum approaches to this. The continuum approaches, they have inherently to make certain assumptions about what regime you're in. Are you in a locked regime, a flowing regime, a gaseous regime? So they're limited. But on the other hand, the continuum approaches don't need to resolve every single grain, so they're very economical. So the question is, can you get kind of a discrete approach that takes advantage of continuum knowledge where it's applicable, but still gets all of the jamming and grain scale effects that you can get from individual grain modeling where you need it? And can you do it without the user having to prescribe where each thing happens? In other words, by having an error criteria, an error metric to determine where to adapt your domain. And what's, again, that's the practical side of it. What's neat for me, the part that I'm attracted to, is kind of the underlying coupling principle. We start from Lagrangian mechanics sort of approach. This is one of those granular simulations. We start from a a Lagrangian mechanics approach. You always use bunnies in graphics. Maybe I'll take this away for just a second. So you start from a Lagrangian mechanics approach and you say, what if you wrote down the same Lagrangian twice, redundantly, and then you weighted your system, X% by this Lagrangian, X% by this one, considered them simultaneously, so you wrote this combined Lagrangian. Of course, you can show that doesn't change the solution, so it's a mathematical triviality, but it opens the door to now using different discretizations for these two Lagrangians while maintaining the appropriate communication between them in a principled manner. So that's the basic idea. So that's one thing. I think more broadly, me and you are working on kind of understanding discretizations of Laplace operators, and sometimes I think of what's my 10-year vision, and I come to the conclusion that I really like to work with my students to identify a problem rather than coming and saying this is the next problem. So it's very organic depending on which student and what their background is and what their interest is.
So Eitan, I love your work. I'm always curious. So you work in this kind of piecewise linear discrete setting, right? And then when we go and we render things, for instance, you really want that smooth curved surface back, so we fit a bunch of things. So how does this notion of preserving these geometric structures in this piecewise linear setting, can you extend it to sort of like a...
Well, there are people, so there are people who take things like discrete exterior calculus and they think of Plec, like these polynomial or higher order exterior calculus approaches, which could be somewhat interesting from a convergence standpoint. They can converge faster. For me, in that sense, I'm not very practical. In that sense, it's more of a principled sort of Puritan way of thinking, which is I want to go as discrete as possible because I want to kind of find out what are the fundamental obstructions to discretizing this thing, or what are the very basic structures that need to be carried over. You can ask the question, why do that if you're going to smooth things out when you render them? And I think the answer is that, for me at least, is that if your discrete system can be run at fairly coarse discretizations and preserve whatever structure is important to the system, then when you smooth it out, you're still going to see the benefits of that in a way that if you just ignore that, you won't.
Let's thank Eitan again. Eitan will be here the next 2 days, so shoot me an email, Alec Jacobson. If you'd like to meet with Eitan, we'll probably squeeze you into the schedule.